Okay, here's review video number 10. It's all about magnetism. Now basically, the thing you need to know is that there's a magnetic field around every magnet and any moving charge. Okay, that's kind of what electromagnetism is all about, that any magnet has a magnetic field, but also any moving charge, any electron that's moving, so current exerts a magnetic field also. So magnetic field is a capital B. And the direction is the direction that the North Pole of a compass points. So if we have a typical magnet, bar magnet, let's call a South Pole and a North Pole. Okay, we draw the magnetic field lines around that. Okay, just like any other field lines, they never cross, and they should be touching. They shouldn't be touching, even though mine are right here. It's kind of hard to draw. Okay. And if we put a compass at this point, the north end of the compass would point away from the North Pole of the magnet. Okay. If we put that compass over here, the north end of that compass, which is usually the shaded one, would point away from the North Pole of the magnet. So the direction is always out of the north, away from the north, into the south. When it's outside, oops, those are backwards. When it's outside of the magnet. When it's inside, it comes back around through, and then kind of completes the cycle. All right? Now, magnets are always strongest at the poles, and weakest out towards the middle. So wherever those magnetic field lines are closest together, that's where it's going to be the strongest. And then just some basic 4th grade stuff here. Okay. Like poles, like two south poles, would repel each other, so their magnetic fields would look something like this. Okay. Two north poles would repel each other, and they would look something like this, going away from the North Pole. Okay. And obviously, opposite poles, the north and the south, would attract each other. So it would look something like this. Okay. Basics of magnetic fields. Also, Earth has its own magnetic field as well. Okay, so if this is Earth, now where it gets a little bit tricky is that even though we call this the North Pole up top on Earth, it's actually the magnetic South Pole, which is why our compass needles point north. So realistically, our magnetic field around Earth should look like this. Okay? It's kind of contrary to what you would normally think. Now the whole reason why magnets are what they are is because the little tiny electrons, groupings of electrons called domains, inside a magnetic material, they kind of brick together like this a little bit. All of these things spin in the same direction in something that's magnetic. If something is not magnetic, they spin in all different directions. So maybe one is going this way, one might be going up. Okay, so it's all about the direction of those domains and the directions in which they're spinning. Now a little bit about electromagnetism. And this is just a real quick review because there's not a whole lot of magnetism on this test. Basically, if you have a wire, okay, that's carrying current, there's going to be a magnetic field around that wire. All right. So any sort of moving electron creates a magnetic field. Okay. But if a magnet, let's say we have a loop of wire here, and we drop a magnet through it, as that changing magnetic field goes through that loop of wire, it's going to force electrons in that wire to move. This is all electromagnetic induction. So anytime a magnet creates a current, or current creates a magnetic field, that's electromagnetic induction. Okay, good vocab word to know. That's really about it for magnetism. It's very basic stuff. None of the right-hand rules are on this. No force in a current carrying wire. It's very simple, easy stuff on the regions in terms of magnetism.